and welcome to episode number 12 of CS350 Online. I'm your host, as always, Leslie Ested, and in today's episode, we are going to continue our discussion of virtual memory, which I'm pretty sure most of you have forgotten about, so we'll do a brief review of that first. And then we are going to keep talking about more virtual memory, because it's a pretty big topic. So that's what we're doing today. One thing I did want to remind you of, if you haven't already gotten started on assignment 2, please do get started. Because even though it probably seems like we spell all the details out, what you're going to discover is that even though we might spell a lot of the details out, when it comes to debugging, it can actually be a very tricky assignment. So you might spend, a day or two writing the code, and then you'll spend 3 weeks trying to debug it. So to get started on that. Now, first, of course, we have the OS of the day. So today's OS is called Alto Executive. This is a really cool operating system. This was released in 1973, and it is a product of Xerox PARC, which some of you may have heard of and some of you may not have heard of. But this operating system in particular ran on a piece of hardware called the Xerox Alto. And the Xerox Alto, you could almost consider it to be one of the very first personal computer. And this is actually a photo of it down here. I know you can't see it because of my chair kind of being in the way. But this is like a size of a filing cabinet on wheels. It's actually quite small. And so that's the CPU. That's, your desktop. It's like 2 desktops side by side. It's not that big, actually. I feel like it's a very reasonable size machine. I'd love to have one, I can tell you that. And then you've got a keyboard, and hey, look at that, it's 1973, and there's a 3-button mouse, and we'll talk about that in a minute. And then there's a monitor, and you might be thinking that monitor looks awful funny because it's in portrait mode, not landscape, but this is actually correct. This is the way it was supposed to be. So this is a whole computer unit, and effectively the first personal computer. It had Ethernet connectivity, so you could actually have LAN parties with it, and in fact they did. And it did have a 3-button mouse, and a device that you can't see in the photo is it also had a 5-button chord keyboard. So if you wanted to play music, you had a little 5-chord keyboard. That wouldn't have been a feature I used because I can't play music. So what else? So that's the piece of hardware. Now, what about the operating system? Now, the operating system was fairly modern for the time. It had, preemption, time sharing, and things like that. But there's a few things that were really notable about Alto Executive. And you can see we kind of have it down here at the bottom of the slide in really big uppercase letters. It says it had a mouse-operated GUI. It means that it actually had a desktop environment where you double-clicked on things in order to open programs, and you could drag and drop and navigate things with the 3-button mouse. And that's actually the really big thing that Alto Executive brought to the table. And in order to make that work and not take a really long time in order for it to, respond to events, they had to kind of blur the lines a little bit between user and kernel privilege. So a lot of the user applications were allowed to access microcode so they could optimize and so that they could get really good performance out of this. So keep that in mind. They had to do a little bit of tinkering. They weren't really developing this machine for security purposes. They were developing it for use in an office so that you could do office applications. Now, it had full Ethernet and LAN support, and it actually had a number of games. And some of those games you could actually play on the LAN, and people at Xerox PARC actually had these machines, and they would play LAN games on these machines. So the first LAN parties, well, here you go. All the way back in the 70s. And the code for this popularized Camel Case, which is a product of Xerox PARC, along with many other things, like LAN. So what is Xerox PARC then? This is something that's actually worth mentioning. So Xerox PARC is probably one of the most famous computing research centers in the world. So there's also, of course, Bell Labs, which you probably know because that's where Unix came from. But Xerox PARC is another one of equal fame, and you can thank them for a lot of things that you use every day. For example, you can thank Xerox PARC for things like object-oriented programming. And you could thank Xerox PARC for laser printers. That one's probably kind of obvious considering it's obviously Xerox. You can thank them for GUIs and the desktop paradigm. You can thank them for, I mean, to be honest, we could go on here forever. Xerox PARC is a very, very famous research facility. And by the way, this place still actually exists, and they do take interns, so co-op students, you are welcome to apply there. And where is it? I know it's kind of irrelevant right now because nothing we are doing is actually in person. Everything, of course, is remote. But PARC stands for Palo Alto Research Center. So Xerox PARC has a location. Its primary location is in Palo Alto, California. So yeah, that's a pretty cool place to be. I can tell if you have something like Xerox PARC on your CV that people would take notice because it's a pretty famous facility. So it's pretty cool, especially if you're interested in computing research. That is definitely a place you would like to be a part of. All right, now at the bottom here, I got a couple cool things. So here are some icons from the original desktop environment. And don't they look familiar? Like, here's a folder and an empty document and a printer and a trash can for your garbage. And wait a minute, those are pretty much the same icons that we use today. They go all the way back to the early 70s and Alto Executive Operating System. And what's actually neat is, so these computers, there weren't that many made. I think there was only like 2,000 of these made. And it's really hard to get your hands on one and really hard to get them working these days. Just keep in mind, they're 50 some years old now, 60 years old. Anyways, so it's really hard to get your hands on these and get one that's actually working. But even when they were first created, they were really, really expensive. So most people like Steve Jobs can actually afford one of these. So he actually went to PARC and he was really inspired by their desktop environment. And a lot of the inspiration he got from Alto Executive shows up in the macOS desktop design. So this has been quite an influential operating system on the desktop environment you use today. I mean, if these icons are anything to show. And here's a couple pictures of it running. Yes, it was a black and white dithered screen. Dithering is a dot pattern that is used to convey tone or shade. So what's really neat about this is, look, you got like a system browser and there's some code open and it looks like it's Smalltalk, which is another product of Xerox PARC, I believe. It's an object-oriented programming language, and Objective-C is like Smalltalk combined with C, and it's really weird. I don't like it. Don't like to admit that I know how to program in it either. So you've got overlapping windows that you can drag around, and you've got code browsers, you can send emails, you can show images, and look at that, there's the little mailbox icon. This kind of reminds me of the TWM desktop environment. There's a calendar and a clock. And then here's a really popular test image that they had where they were playing with fonts and different dithering patterns to represent colors. So it's really cool, right? I think it's really cool that this was back in 1973. All right, I'll stop ranting about this cool thing. You have to understand, as someone whose primary research area is computer graphics, this is a pretty cool OS for us, obviously. All right, so today we're going to have a pretty big recap because I'm pretty sure everybody's forgotten where we were. I know I probably forgot where we were. So let's go back to talking about virtual memory then. Sorry, I've got some new lights for my green screen. So what if you're seeing this funny little thing here, it's actually a shadow. And it's just because I don't have an extension cord for my new light. My light actually needs to go behind me to stop the shadows. And the cord's not long enough. Fix that for next class. All right, so we were talking about virtual memory, and let's go back to the beginning so that we can remember, because we did an A2 break, and then we had reading week, so it's been like almost 2 weeks since any of us have really thought about this. So virtual memory is we've been talking about this practice of abstracting the user program from the actual hardware and from the kernel itself. And virtual memory is kind of one of the last steps to that. And what virtual memory is we're going to give the user programs fake addresses to use. And there's really good reasons for doing this. One of which, I mean, some of them we talk about here, it's going to isolate the processes from each other. Because if a process is using the real addresses on a system, then by virtue of knowing where you live in memory, you know where you don't live. And if you know where you don't live, then you can start playing with those addresses that don't belong to you and potentially get secure or important data from other processes that we probably shouldn't be accessing. So when we use virtual memory, because all processes are going to be mapped to the same fake address range, each process will believe it owns all of memory. It won't know where it actually lives, and it thinks it has all the memory, so it can't actually search around to find other processes. So that's a pretty cool feature. So virtual memory can be used to isolate processes from each other. It also isolates processes from the kernel, because the kernel will also use virtual addresses, but it's going to use a different range. And that's going to actually come into play at a hardware level, because if we are running in user privilege mode, and remember, privilege is actually something that is set in hardware. It is a feature of the architecture, not just some kind of logical thing we're implementing. And if you're executing code in user privilege, and then all of a sudden you get a kernel address, which is going to be completely different from the virtual addresses used for user process, then the hardware will know that you're trying to access memory you're not allowed to, and it can throw an exception and prevent you from doing that. So that's actually a pretty cool thing. So the virtual memory is going to isolate processes from the kernel. Now, interesting thing, and I know I promised that I would post the links to these. I will get to it. I'll make a note to myself. The Meltdown Inspector papers. Those are bugs that came out maybe 2 or 3 years ago. I'm not quite sure on the exact date. But those were bugs that were found in the Intel architecture that were letting the user program perform a certain kind of cache attack, and actually get privileged data. And what they were doing is they were taking advantage of the fact that modern CPUs rearrange instructions, and they might actually access data stored at kernel addresses and put it into the cache before we've officially made the switch from user privilege to kernel privilege. So that when we make the switch to kernel privilege, we'll validate the instruction, and then it's already in the cache, so it's a faster thing. The problem is that with the Spectre and the Meltdown bugs, what was happening is they were doing a timed cache attack, and it was letting them get the privileged data out of the cache while still in user privilege mode. Now, my understanding is Intel actually released a patch to fix this particular bug, but their architecture actually took a pretty significant performance hit, which is why when I purchased a research machine, I actually went for the Threadripper AMD's architecture instead, also because it was cheaper. But there you go. All right, I'll post those papers for anyone who's really interested to see how they work. It's actually kind of cool. So that's one of the reasons why we use virtual memory, is to isolate things from each other. Another reason why we use virtual memory is so sometimes we don't actually have a lot of physical memory on our computer. So for example, this Mac here that I'm using has 32 gigs of RAM, which in my opinion isn't enough memory. I could go through that in probably about 2 minutes. Some of the images that I work with are multiple gigabytes in size. And if I'm working with like raw film footage, like I think I've got some footage on my computer. What do I got? I got some from Godzilla. And I've got some footage from the sequel to 300 as well. And when you load raw film footage, it's really big. Really, really, really big. You're talking like multiple gigabytes in size. So running out of memory is really easy. So your program might actually need more heap space than you actually have physical memory. And virtual memory will let this work, because what happens is you can have an address space that's technically bigger than the amount of physical memory that you have. And how it works is the implementation of virtual memory will simply span from not only physical memory, but it will also pass into your disk space. So we can actually store part of the address space on disk. And by the way, if you're any kind of Unix user, Linux, anything like that, you know this is swap space. And what swap space is generally used for is when the address space is too big for physical memory and we want to put some of it on disk. So we have a special partition set aside for this. And now swap space isn't that big of a deal these days because we generally have a lot of RAM. But in the the late 90s, if you were a Linux user back then, or the early 2000s, which I was, and it was really important that you actually had a swap space that was at least as big as your RAM. Which, at the time, I think I might have had maybe 512 megs RAM. So it was really important to do that so that you could support address spaces that actually were too big for physical memory, and you could swap part of them out into the secondary disk storage. We'll talk a lot more about that in a day or two. So virtual memory supports address spaces that don't live entirely in RAM, but also on the disk. And the other cool thing is that maybe it's not the particular address space of this particular program that's too big, but maybe the sum of the sizes of all the address spaces that you're using right now, maybe them all added up together and add up to something that's bigger than the amount of physical memory that you have. And virtual memory has ways of swapping some of those out to disk so that we can actually make it look like we have more memory than we really do. So that's really cool, and we'll talk more about it. So that's why we are doing virtual memory. And this concept of virtual memory is not new at all. It actually goes back to 1956. So we've been using this idea, or at least had this idea for a very, very long time. Now, of course, the big problem that we talked about before was that if every address is fake, right down to every jump, every branch instruction, even the program counter is fake, then how would the CPU actually know where to get the next instruction from? Because it's not even a real address. Well, then you're going to have to be translating every address before the CPU uses it. And, one idea is to have the kernel of the operating system do that, but that would be an exception, at least one exception for every single assembly instruction. And that's just not feasible. So what we actually have in the hardware is this thing called the memory management unit, or the MMU, and it's going to take each address and it's going to translate it from a virtual address to a physical address so that the CPU can actually use it. And the memory management unit will be managed by the kernel because the kernel is responsible for actually implementing the details of virtual memory. Now, we talked about a couple virtual memory schemes. We talked about dynamic relocation, which is a really, really simple scheme, and it adhered to the three principles that we really liked, which was it offers protection, it offers isolation, and it also is very efficient in terms of both time and space. So all that virtual memory or dynamic relocation did, if you remember, was you have a contiguously allocated address space in virtual memory. And we are going to find an equal-sized contiguous block of physical memory, and we're going to map this to that. And so for each process, we store an offset, which is where does this address space start in physical memory, and a limit, which is how big is it. And then to do the address translation, you check if the virtual address is less than the limit, because we want to make sure it's a valid address for this address space. And then if it is a valid address, then we simply add the relocation or the offset back to it, and we're done. So 2 integers are stored per process to make this work. And it's just adding and subtracting to translate between the two. So it's very, very efficient. Very, very efficient. It offers protection. It offers isolation. But we don't use this method in practice because it suffers really heavily from fragmentation. Now, if our address space was contiguously allocated like you see in this picture here, like all the code, the stack, and the heap are all tight together, we would have this problem of external fragmentation where each allocation of each address space is a different size, and we may run up with a problem where we need 20 megs and there's no 20 meg contiguous block. And so the only way to actually to handle that is to either say you can't start this process up, or to defrag RAM. And defragging RAM is not a cheap process. And you learned a little bit about defragmentation methods in CS241, you may not remember, but it's actually a pretty costly thing because you're going to have to shift everything over. And when you shift everything over, you've got to update all those values, and it's just a pain. Now, the truth is our address spaces aren't laid out in that way. Our address spaces were actually laid out more like this. So if this is our range of virtual addresses for a 32-bit virtual address, in OS 161, and this, even though we're using an OS 161 example, I want to tell you that this is also true for Windows. This is also true for Linux, and this is also true for Unix and Mac OS and BSD and iOS. So your stack actually lives in the very middle of the virtual address range, such that the high end of the stack is usually this 50% point. We will explain why this is a little bit later, but not today. Just trust me that this is the way it is, and if you want proof, make a bunch of programs on your different operating systems and print out the address of the stack, and you're going to see that the stack is, aside from address space layout randomization, the stack is roughly located in the middle of the address space. And then your code segment is going to be at the front, and then the data and the heap is going to be just somewhere around there. So if we were to use dynamic relocation on a real address space, because it has to be a contiguous allocation of addresses, we would actually have to allocate from 0 to the 50% mark. So each address space would be 2 gigabytes in size, just going from 0 to the halfway point. So we wouldn't have external fragmentation, but we do have pretty serious internal, where we've got all of this memory allocated, but we're not actually using. So this is the sort program in OS 161. It technically only uses about 1.2 megabytes of memory for its address space between the 3 segments, but we'd have to allocate 2 gigabytes for it. So dynamic relocation is going to have fragmentation, and it's going to restrict the number of processes you can actually run. So that doesn't work. So our improvement to that, of course, was to do segmentation, which is kind of doing dynamic relocation, except on each of the segments of the address space. That required us to split the virtual address into 2 parts. The first part being the segment number, and the second part being the offset within this segment. So the segment number is going to identify, is this code, is this data, is this stack? And then the second part of the address is indicating where in the code, where in the data, where in the stack is this address. And so we store offsets and limits for each of the segments. Excuse me. And then when we do the address translation, the MMU has to separate off the segment number. When it gets the segment number, it will then look up the appropriate offset and limit for that segment. And then if the virtual address is greater than or equal to the limit, then we know it's not valid, i.e. it's an exception, which is actually where the term segmentation fault came from. But if it is a valid address, then we simply add the offset for that segment, and that's how we get the address. So very similar. This one is going to eliminate internal fragmentation, but it doesn't eliminate external fragmentation because each segment has a different size. So we're going to still run into that problem. Now, this was actually, even though this suffers from external fragmentation, segmentation was actually used in the early versions of Windows for their virtual memory implementation, and it wasn't a big deal. The reason why it wasn't a big deal in things like Windows 3.1 was maybe you've used Windows 3.1 before, maybe you haven't, but you're looking at an era of like 386s and 486s, and those computers, you realistically weren't running multiple programs at the same time. Like having 2 Netscape navigators open at the same time, that was not an advised thing to do. It's simply you didn't have enough computation power to do it. So you're looking at an era where it was rare for people to have multiple programs open at the same time. So this concept of fragmentation never really came into play. Also, programs were so small back then. Like when I had a 486 that ran Windows 3.1, I only had 30 megs of RAM. And that was enough. So, yeah. It was okay back then, but it doesn't work today. All right. Now we wanted to solve, and this is kind of where we left off, we wanted to solve the fragmentation problem. So we wanted to make sure that each allocation of physical memory was identical in size, so we didn't have external fragmentation. So what we decided to do was to logically, that is in code, subdivide physical memory into equal size frames or physical pages. And typically you're going to see the size be 4 kilobytes. That's the most common size. And then what we're going to do is we're going to do the same thing to our virtual memory. We're going to logically divide virtual memory into equal size pages. And the page size is going to be equal to the frame size. And then the whole idea here is we want to, instead of asking for 7 contiguous pages of physical memory, we just say, give me any 7. So each individual page of virtual memory can map to any random frame of physical memory. And so since now allocations are all of equal sized, we have eliminated external fragmentation. Now we still have internal fragmentation because we don't have the concept of a partial page allocation and we don't share pages. But let me ask you this. So if our page size is 4 kilobytes, which by the way is probably the page size your computer's using, it's the most common one. So if you've got like 32 or 64 gigs of RAM, and let's say that you've got address spaces with 5 segments, each segment could waste, maybe 3 kilobytes. So that's 15 kilobytes per process. So 15 kilobytes per process, and you've got maybe, 100, let's say 200 processes. So you're wasting internally maybe 30 megs of space. Who cares? It's 30 megs out of 32 gigs. I'm not going to care about that wasted space. So yes, paging does have internal fragmentation in the sense there's internally wasted space, but it's so small compared to the size of modern memory that we just don't care about it anymore. Now, one of the problems with paging is the translation. So we haven't really talked much about the translation, and that's where we're going to continue today. So let's switch over here to this so we can talk more about that. Horrible shadows. I have green screen. All right. So in order to do the translations for paging, what we actually have to do is we have to store a page table. Now, the example on these slides shows you that the address space is continuously allocated. We know in reality there's code and then there's data and then there's a stack somewhere else down the way. So here's the thing. Because the address space, the pages we are using are not contiguous, our page table must have an entry for every for every page in virtual memory. Not just the pages that we are using, but for every page of virtual memory. And then in each page table entry, we have to know whether we are using that entry or not. So we keep something known as the valid bit. So if that page table entry is in use, then the valid bit is 1. And if it's not in use, the valid bit is 0. Now, again, if your address space was contiguously allocated, you wouldn't need to do this. But ours is not contiguously allocated. You've got code and then heap somewhere else and then stack way off somewhere else. So we actually need to have one entry for every page of virtual memory. So in our example from the notes where we have 16-bit virtual addresses, we are going, and 4 kilobyte pages, our page table has 16 entries, regardless of how many pages we are actually using. Okay. Now, maybe you don't see this as a problem, but it is a problem. So what that for our sample, we have a page table with 16 entries. But how do you compute how many pages there are in virtual memory? So let's actually switch over here to OneNote. Which of course has crashed. I asked people for suggestions for before on different tools I could use for this note writing, and I did try some out. But I don't know if the pen driver is buggy or what, but it didn't work. So I guess I'm stuck with buggy stuff. I could use the GIMP. GIMP does work, but I don't feel like it. All right. So what we've got is to figure out how many pages you need, page table entries you need, is the same as figuring out how many pages are there of virtual memory. So the number of pages in virtual memory is equal to the number of page table entries in your page table. And that is equal to the VM size, your virtual memory size, divided by the page size. Let's abbreviate things here. So if you use V bits for the virtual address, it's 2 to the V divided by the page size. So in our course notes, our number of page table entries in our page table is equal to 2 to the 16 divided by 2 to the 12. 2 to the 12, by the way, this is something you should remember. 2 to the 12 bytes is equal to 4 kilobytes. That's a really important thing to remember. So this means we have 2 to the 4 PTEs, page table entries, or pages in our virtual memory. So that, of course, is, everybody knows, is 60. Okay, so that's not so bad. But let's start looking at modern memory. So the computer I had some number of times ago. So let's look at the computer I had in 2000. So I'll say my copy from 2000. It's a really long time ago. It had V equal to 32. So it was 2 to the 32 divided by 2 to the 4, or not 4, 2 to the 12. That means that I had 2 to the power of 20 page table entries. Now, that's a really big page table. I mean, you're talking about a pretty big number here. Like, let's see. Let's get out a Chrome window here because they don't have a calculator handy. So let's say, oops. We're not supposed to be looking at a Breath of the Wild video. 2 to the power of 20. So that is, you know, that's over 1 million entries in our page table. And maybe that doesn't seem like a big deal to you. But this computer, my computer from the year 2000, had 512 megs of RAM. And you're telling me every process's page table had over 1 million entries in it. Each of those entries takes up a certain amount of space, which means those page tables might have been a few megabytes each. And with only 512 megabytes of space available, I kind of don't like that. Now let's look at modern computers. Modern computer. So virtual, even though they are 64-bit architectures, we typically use 48-bit virtual addresses. So that is 2 to the 48, and we still typically use 4 kilobytes for page size. So that leaves 2 to the power of 36 page table entries. How big is that? Let's open up that calculator there I have. So that's 2 to the 36. Okay, let's get Google to do the math. Oh my goodness, that's 68 billion entries in my page table. Now, if each of those page tables are, let's say, 4 bytes in size, but that 4 bytes is probably a little small. So let's say 8 bytes. That means that each page table is 549 gigabytes. but my program Hello World has an address space total size of 2 kilobytes. So this is a problem, and we'll solve this in a minute. So paging does solve external fragmentation. And the internal fragmentation, the internal memory loss, we don't really care about. But paging does have this problem of creating page tables. They're absolutely enormous in size. Okay. We'll deal with the size later. What I'd like to do now is look at how do you do the address translation. So before we solve this problem, let's translate the addresses, because we haven't talked about that yet. So let's go back to this slide. So how do we translate the addresses? Well, our MMU is going to have a single register, and that single register is going to be the page table based register. It's going to be a pointer to where in RAM you can find the page table for this process. And inside the page table, we have a mapping between so entry 0 would be page 0, and it would contain which frame number page 0 maps to, and it would also contain a valid bit. We would look at the valid bit, and if the valid bit was 0, we throw an exception because it's not a valid page. And if the valid bit is 1, then we're going to do some magic to do the address translation. So we first have to separate the page number from the page offset. You can get the page number by taking the virtual address and dividing it by the page size. And you can get the offset with the address within the page by taking the virtual address modulo the page size. Now, this is all hex math, and we probably don't want to do that. But let's suppose we have separated the address into page number and page offset. Then the physical address, and we've looked up our page table entry, the physical address is the frame number times the frame size plus the offset. I want to show you another way of looking at this. So our addresses have two parts. The highest order bits are going to be the page number, and the lower bits are going to be the offset within the page. Now, what we're going to do is we peel off the page number bits, and we use that to look up the frame number in the page table. When we get the frame number from the page table, we drop the frame number into the highest order bits of the physical address. And then adding the page offset is the same as just dropping the offset bits down into the lower bits of the physical address. So that's pretty cool, right? If you look at this from the perspective of breaking down the bits of the actual address, it's actually much easier than doing things like calculating the virtual address modulo the page size. Nobody wants to do that in hex. But now we have this problem of how do we figure out how many bits we need for the page number and how many bits we need for the page offset? Well, the good news is there's a really easy formula to do this. So the number of bits for the page offset is the log, and these are all base 2, of course, of the page size. So because we are using 4 kilobyte pages, the log of 2 to the power of 12 is 12. So 12 bits, the bottom 12 bits of the address are going to be the offset within the page. So that's fairly straightforward, right? I don't think that's too bad at all. And then to figure out the number of bits we need for the page number, first we need to know the number of page table entries in our page table, which we just showed you how to calculate. It's the virtual memory size divided by the page size. And then we take the log of the number of page table entries, and that tells you how many bits you need for the page number. Now, why are we doing that? Because we want to know how many bits we need to index each of the entries in the table. So that's why taking the log is going to work. So for our little example here, we need 4 bits in order to do that, because the log, if we go back to OneNote here, this is right here. This is how many page table entries we have. So the log, and again that's base 2 of 2 to the 4, is 4. So 4 bits for the page number. And the page number is always the highest order thing. So using this bit manipulation, you'll find it's much easier to separate the page number and the page offset. And then what you're going to do is you just drop the bits down for the frame number, or you grab the frame number, shove it in the highest order bits, and then drop the offset down. Because the offset for the page and the frame are going to be the same. It's pretty cool, right? I think it's pretty cool. I'm not sure what my computer's doing right now. Oh, don't rest your pen on the tablet. It's a bad idea. It rolls around and makes your mouse behave funny. Okay. So now that you've seen how to actually do this translation, let's actually go through a few translations here ourselves. So I'm going to do this for process A, and I'm going to let you do it for process B on your own. So here's our new page. Let's get some nice lines down. Okay, so we have, some colors here. Here's our virtual addresses. So 0102C. And we should calculate our page number. And here's our offset. And then the physical address we'll put here. So what is the page number for 102C? So we know that the page number is the highest 4 bits. Now remember that this address is presented to us in hex, and what this address really is in binary is this. I'm going to have to do this on 2 lines here because I don't want to waste too much space. And I don't remember C and binary, so we're just going to do 4 dots. Epitome of laziness. All right, so what that means is our page number, because it is the highest order 4 bits, is these 4 bits here, which 4 bits per hex digit, we're lucky, it just means whatever hex digit we see here is our page number. So this is going to be page 1. And then our offset is the remainder, the remaining 12 bits. So my offset is 0 to C. Now, we sometimes drop the leading zeros. Remember that even if we drop the leading zeros, that means they're still there. We've just dropped them for the sake of laziness. So now what I'm going to do is I'm going to look up page 1 in my page table, and I see that it is valid. And so I'm going to drop my frame number in, just like this. And then I'm going to drop my offset. Ta-da! We have translated the first address. So now let's go to the second address, which is 9800. Now again, remember that the page number is the first 4 bits. So in this case, the page number is 9. And the offset then is 800. So I look at my page table and I see that due to the way this address space is allocated, I can anticipate that page 9 is invalid. So we actually get an exception. And then for the final address, 0024, my page number is 0. And my offset, and this time I'll draw the leading zeros, is 024. So I look at page 0, and I see that it is valid. So then I'm going to do 0xF024. There we go. We have translated those addresses. I'll let you try them for process B on your own just as good practice. But hopefully that makes good sense to you as to why doing this bit-based method is much easier than dividing and doing modulo with hex. All right. So there you go. Now you know how to translate. All right. So we've already kind of alluded to this topic, but now we're going to go into a little greater detail about just how big the page table entries are and just how big page tables can really be. So a page table entry doesn't just contain the frame number and the valid bit, because there's actually more information we need it to have. For example, the code segment should be read-only. Nobody should be allowed to overwrite the code segment. You also, if you have a segment for global constants, you don't want that to be written over either. So some of the segments of our address space need to be read-only. And so in order to make sure that we keep track of that, pages which are read-only, we need to indicate that they are read-only. So a page table entry needs to also have something like a write protection bit. And that way, when the MMU is translating an address, it will actually know if you're trying to load or store from that address. And if it sees you trying to write to an address that has a write protection bit set to 1, it will be like, yeah, you can't do that, exception. So Our page table entries need to contain bits for things like write protection. They also, because we want to keep track of usage or whether pages have been written, and this comes into play when we were talking about on-demand paging, we have other bits to track how often pages are used and if they've been written to and so on and so forth. So each page table entry can actually have a lot of information stored in it. So these page tables, they might have 68 billion entries, but each page table entry might be 8 bits inside, or not 8 bits, it might be 8 bytes. So you could actually have page tables that end up being gigabytes in size. So this kind of becomes a problem because where do these page tables get stored? They get stored in the kernel's memory. They get stored in RAM. But that would mean that my page table on the computer sitting in front of me is bigger than the amount of RAM I technically have. That's going to be a problem. So page tables, they offer protection, they offer isolation. In terms of efficiency, they are very efficient in terms of time. The calculation is quite simple. But in terms of how much space you need in order to store the information, they are really not efficient. So we need to solve this problem. So how do we solve the problem of a really large page table? Well, we could organize it. So let's think for a moment now, not about paging, but let's think about a directory. So I'm going to open up a directory on my laptop, and you can laugh all you want. My downloads folder is horrible. Of course, I can't find it. All right, well, let's just do this, and let's go into my downloads folder. Okay, my downloads folder is full of stuff. When I download something, I put it in my downloads folder, and I have a tendency to forget about it. Or I forget to delete it when I'm done with it. But when you were a kid and you were downloading stuff off the internet, maybe you were using Napster, maybe you were using LimeWire, or BitTorrent, I don't know, whatever you were using, you probably downloaded it to the desktop or to the C drive, and you forgot about it. And so you end up with this directory that has everything in it. So you get billions of files in it. Finding anything in there is really hard. And so how do we organize it? Well, how do we solve it? How do we make search in a directory faster to find our file? Well, we would subdivide the files into subdirectories. And one of the ways that you could do that is, every file that starts with an A goes in the A directory, and every file that starts with a B goes in the B directory. But if you have no files that start with a J, why would you create a folder that starts with a J? Well, that's a good point. So if that region has nothing, then don't bother creating any of the data structures to store it. And that is kind of the idea we're going to use with the page tables. We are going to create that's not what you want. We are going to create multi-level page tables. And the idea is, so we're going to have this page table tree, but we're only going to create the tables in the tree where there is at least one valid entry. So if there is a region of the address space where there's no valid entries, i.e. the area between the heap and the stack, why create page tables, subtables, for that region when there's no valid entries in there? So that's what we're going to do, is we are going to create this organizational tree, and any region that has no valid entries, don't create that part of the tree. So we are going to be shrinking the amount of page table entries we have in doing this. Now, the one thing I do want to say is this perfect? So is a multi-level page table always guaranteed to be smaller than the single level page table? No, actually it's not. So here's an interesting story. So let's suppose you have a virtual memory that is 48 bits. So you have 2 to the power 48 bytes possible virtual memory. And let's suppose that your address space uses 100% of those addresses. The single level table will be smaller than the multi-level table. Because the multi-level table, how it works is your page to frame mappings only appear in the leaves. And all of the internal nodes of the multi-level table are saying, okay, well, this, if you are if the first level's page number is this, then here is a pointer to the next level's page table. So all of the internal nodes are extra tables that you're creating that don't actually contain page to frame mappings. It's only the leaves that contain them. So if you use 100% of your virtual memory, it's all valid, then the single level table will actually be smaller than the multi-level table. But in practice, that doesn't happen. So in practice, the multi-level table is smaller. I'm just saying, from a theoretical perspective, multi-level tables are not guaranteed to be smaller than their single-level counterparts. There are situations where they will be bigger. So I'm not going to tell you quite yet how we divide this, but I want to show you an example of why this is cool. So here is our single-level table from before. And I'm going to, when we create a multi-level page table, instead of having one page number, we now have many page numbers. We have one page number per level of the tree. So I am going to take my single level page table from before and I'm going to convert it to a 2-level page table. So I go from 1 page number to 2 page numbers. So if there are no valid entries in the subtable, then I don't create that. So subtable. So I have page to frame mappings for the first 7 frames, or first 7 pages. So the last 2 pages, there's no valid entries in these lower ones, so I don't create subtables for them, and their entries in the directory or the root of this tree are going to be null, and the valid is going to be 0 because that doesn't exist. So what happens then is if I'm trying to translate an address on, let's say, page 1, then I am going to see, okay, page 1, I'll get that page 1, it's table 2, and then in table 2, let's say, sorry, not page 1, let's say we're trying to translate like page 8 here, or not page 8, let's do this page right here, this page right here. So then I get my secondary page number is that. I'll explain how we get that in a minute. And then I get my frame number. So I have to do 2 page table lookups. So instead of just doing 1 page number to 1 frame mapping, I have 2 page numbers. So I use the first page number to look up the address of the table in the root, and then I use the second page number to look up the entry in the second level table. So what my address looks like now is my address is page 1. So page number 1 and page 2, and then the offset. So this is, we'll do the lookup first here. And then once we get our table for that level, then we do the lookup second in a different table. So that's kind of neat, right? What does this all mean? Well, when I create this 2-level page table, what's really, really interesting is that, so we had 16 entries before, and now my page table only has 12. Over 50% of the entries in the single level table were invalid, so useless. But if we look at 2-level paging, of the 12 entries, only 3 of them are invalid. So we have fewer invalid entries and fewer total page table entries in total. So in theory, or at least in practice, multi-level paging is going to create smaller page tables for most address spaces. Now we've glossed over a lot of details, like how did we split this up? How many bits for each page number? How exactly do we translate this? And there's a reason for that, and we will come back to that here in a minute. But let's just say, for the sake of discussion, that for the 2-level paging example from the slides, that each page number uses 2 bits. Each page number uses 2 bits. So how lookup works is our address now has 3 parts: the level 1 page number, the level 2 page number, and then the page offset. So how the address translation works is we peel off the level 1 page number. We use it to look up in the root of the tree's page table. and we get the valid bit. If the valid bit is 0, we throw an exception immediately because it's not valid. If the valid bit is 1, we don't get the frame number, we get the address of the next page table in the tree, i.e. the address of one of our children. And then we take the next 2 bits to look up the frame number in the second level. Then we plop the frame number in and to the highest order bits of the physical address, and we drop the offset down. So the address translation for multi-level paging is actually the same as single-level paging. The difference is in how you find the frame number. So the frame number takes a lot, getting it takes a lot more steps because you're going to have to traverse the multi-level page table tree, to find where that page number or where that actual frame number is. Okay. So there's an algorithm here for the address translation. What the MMU does is it peels off the bits for the first page number, does a lookup, checks for invalid. If it's invalid, exception immediately. If it's not invalid, it gets the address of the next table, and then it gets the next bits down, and it repeats the process until it reaches the leaf node, at which point it can actually translate the address. Now, to talk about how do we figure out how many levels and how many bits for each page number, we have to talk about this idea of how big should each subtable be. So we have this desire, and there's a reason for this desire, that each subtable fits on a page of memory. So each page table has to fit within a page. And there's a reason for this, and it's related to on-demand paging, and it's related to disk I/O, and that is that we when we need to load one of these pages from the disk, we want to do one contiguous I/O operation instead of like 8 I/O operations. So we make the size of each page table usually correspond to the size of a singular I/O operation on the disk. We'll talk more about that another time. So we have this desire to figure out, to make sure that each subpage table fits on a single page. Now, for our example in the notes, single level paging is enough because our page table has only 16 entries, and that fits on a 4 kilobyte page, no problem. But if we start to grow our address space, and let's say we now use 40 bits for virtual addresses, we can't fit our page tables onto a single page because there would be 2 to the power of 28 pages of virtual memory, and if each of those page table entries are 4 bytes in size, then I could only actually fit 2 to the power of 10 entries on a single page. So I need to use more than one level. Now you might be like, well, maybe I need 2 levels. And if we do the math again, we realize if I just use 2 levels, then my root of this tree would end up being 1 mega in size. So even 2 levels isn't enough here. So we're going to divide things up so that the number of levels is going to correspond to how many levels do I need such that each page table fits on a single page of memory. Now, the formulas to do this are not in here. So we're going to finish off doing this all over here in OneNote, because that'll make life easier. View page. Draw. No, not draw view. Here we go. Okay. So we need to do some formulas. A whole pile of formulas. So the first thing I need to know is I need to keep track of things like how many bits do I need for the page offset. So the number of bits for the page offset, which we're going to call number offset for now, is equal to the log, and remember these are always base 2, log of the page size. Okay? And to figure out the number of page table entries we have, number of page table entries, well, we don't want to call it that now because we're going to be trying to figure something else out. What I really want to know is how many pages I have. So number of pages virtual memory. So how many pages are in our virtual memory in total? Remember it, that is going to be the VM size divided by the page size, which is really equal to 2 to the V divided by your page size. Now, how many page table entries can you fit on a page? So, the number of page table entries on a page is equal to the page size divided by the PTE size. Now, the PTE size, we will always provide. It's usually something like 4 bytes, 8 bytes, something like that. We are always going to provide that for you. We're not expecting you to figure out how big the page table entry size should be. Once I have all of this information here, I can now figure out how many levels I need for my page table. This is really cool. So the number of levels we need. Now I'm going to write this formula a little bit weird. I'm going to write the inside, then I'm going to write the outside. So it is sorry, I have written the wrong number here. V, which is this V from here, it is V minus the number of bits for the offset divided by the log of the number of PTEs per page, which is how many bits would we need for the page number for in order for to index a subtable. Now this, we're going to take the ceiling of that, and then we're going to take the ceiling of all of this. So round up. All right, so let's give an actual example here. So from the notes, we had V, let's do this in blue here, V equals 40. And let's say that our page table entry size was, let's say 4 bytes. So 2 to the power of 2. And let's say our page size was 2 to the 12. So then my offset bits is 12 because it's the log of 2 to the log of 2 to the 12, and then the number of pages in virtual memory is going to be, so 2 to the 40 divided by 2 to the 12, which gives me 2 to the 28. And then the number of PTEs per page is 2 to the 12 divided by 2 to the 2. So that's 2 to the power of 10. And then the ceiling, let's do the denominator here. So the log, the number of bits I need for a page number then is PTEs per page, is equal to, so that's going to be the log of 2 to the 10, which thank goodness is going to give me 10. So then my number of levels is equal to the ceiling of 40 minus 12 divided by 10. So that equals the ceiling of 28 over 10, which equals 3. 3 levels. Now, if you're having a hard time visualizing how that actually came to be, one of the things that you can do to visualize this is to look at your address like this. So here's my 40 bits, and I know that the lower 12 are going to be the offset. And then what I'm going to do is I know that I need 10 bits for each page number. So I'm going to take starting at the offset and working towards the high bits, I take 10 bits. And then I take 10 bits, and then there's some leftover value y less than 10, or less than or equal to 10 at the front, and there is the final bit. It is okay for a page table to be smaller than a page, but it is not okay for it to be bigger. So there's a pictorial way you could picture how this level formula actually works. So hopefully that's really helpful for you. So there are some sample problems pages I'd like to introduce you to so that for next class we can take up the answers. So the ones that we want to look at are, so there is a paging.pdf, sorry, not path name, paging.pdf, which is single level paging. And then there is multi-paging.pdf, and that is an example for multi-level paging. So take a look at that for next class, and we'll take the answers up to those 2 PDFs. All right, so I do want to leave that here for today, because the next thing that we're going to do is talk about OS 161's implementation of virtual memory, and some other cool virtual memory topics. So next class it will be OS 1's VM, and then that will help you, of course, with assignment 2, or at least understanding some of the bugs you get with assignment 2. And then after that it will be a new topic. So that will probably start not next week, but the week after. So we will see you on Tuesday of next week then. I hope you have a good weekend.